guys are here, that you are healthy enough to be here today. So many of our class are sick, so please do wear your mask properly during class. And again, if you're sick, you can email me and I will email you the Zoom recording of the class after class. Okay. All right. Posted announcement, but just so that everybody knows, if you attended lab 1 last week, you don't need to attend lab this week. If you missed lab 1 last week, please attend lab this week. Your own time if it's available. If you had a Monday lab, you can go to any of them. Okay, so that's just because we have so many people out and there was a Monday holiday, so we decided just to do a repeat, hopefully get everybody caught up. Okay. Any other questions about that kind of stuff before we get started? Yes, please.
So is lab 2 also due? Or
no,
just
lab 2 will be next. So this is just the repeat of last week, so you don't have to go if you already did. Okay, all right. So here is our thought for today. This is Elder Anderson, and he's saying, "How could someone not consider you a Christian?" Reporter asked, and Elder Anderson internalized it, saying, "Does my life reflect the love and devotion I feel for the Savior?" And then he had these 2 other ideas: that the Savior responds to our acts of faith, and that discipleship is not a competition to all, but an invitation to all, a lifelong migration towards a more celestial world. And Elder Holland yesterday talked about what it means to be a disciple of Christ, right, through the atonement. And that is really what we're talking about, is are you centered on that? And when when people see you, are you reflecting the Savior's life? It's not like we're producing our own light. That's not really our goal. Our goal is to reflect the life and the love that the Lord gives us to other people, right? So it's about our relationships, how closely tied we are with them, especially if we're in phase or out of phase, right? All right, any other questions before we start? Okay, as you can see on the handout, we have lots to go through today. So we will start with some review questions. Oh, actually, Elena, I need a copy. All right, but here are the review questions, okay? Does everyone have a copy? Okay. Go ahead and get out your phones or your ABCD cards. Okay, so we can go through these. Okay, this whole first page is review. Okay, before we get into anything new, just trying to make sure we're all on the same page with how we're talking about sound waves, how we're describing it. All right. Okay, so let's start at the top. Okay, nodes and antinodes. We saw before this picture with all of the dots, right? This picture's in your book also, where the dots are really concentrated or really spread out. Those are like the peaks and troughs of the pressure, right? Or the displacement from equilibrium, whichever way you want to think about it. Okay, and then halfway in between is where the pressure is the same as ambient, or the displacement is 0. So that's where it would be a node. Okay, so we have our antinodes are both maximum condensation and maximum rarefaction, and then our nodes are halfway in between those. Okay. Questions about this idea of nodes and antinodes in sound waves? How we relate our dot plots with all the jumble of dots to our idea of waves on a string that's easier to visualize. All right. Okay, so let's go ahead and answer these first set of questions. Okay, these are on on the right column of the upper part of the page. So ABC. Which of these letters is in a region of maximum condensation? Just to see if how the definitions are coming along. Okay, so it is A. Okay, how many regions of maximum condensation are shown in the figure? Just show me your fingers this time. Okay. Good, there are 3. Okay. Then how many pressure antinodes are present? Pressure antinodes. How many pressure antinodes are present? There are 5. How can there be 5? There are 3 maximum condensations. Those would be antinodes. And there are 2 maximum rarefractions. Those would also be the antinodes, the troughs, right? The antinodes are both the peaks and the troughs. Okay, so there are 5 antinodes shown in this picture. Questions about that? That was a little tricky. All right, and which of these letters would be at a pressure node? A, B. Oh, yes, please. Oh, yeah. So let me go back to this guy. Okay. 1, 2, 3, 4, 5. Okay, so 3 of them are at the maximum condensation and 2 of them are at the maximum refraction. Same question over here. Yes.
Yeah, where would the nodes be on that one?
Halfway in between the antinodes. Not really, because it's where the dots are at their equilibrium spacing. They're not super compressed and they're not super stretched out. They're just like what they would be if the wave wasn't there. That's what 0 pressure, 0 displacement would mean. And we can't really see that. We can just know it's halfway between the antinodes. Okay, good questions. Other questions? All right, so last one here. At which letter is at a pressure node, A, B, or C? All right, so the pressure node is at B. Questions about that? Okay, was that a good review? Does that help tighten up some of those ideas? All right, so now we're going to go to, let's see, I'm going to go back to review. Okay, so now these are the next questions. All right. So now thinking about the pictures that we just saw, okay, this is calculate the wavelength of a longitudinal wave, so one of these pressure waves, if you are given the distance between maximum condensations or rarefractions. Okay, so if the distance between a point of maximum condensation and a point of maximum rarefaction is 1 centimeter, what is the wavelength of that sound? Some more. Let's go ahead. If you don't know, guess, because that tells me I need to say it again a different way. All right, so the answer is B. Okay, now let's look at why the answer is B. Okay, because the condensation, which is the peak, and the rarefaction, which are a trough, are half of a wavelength apart. You have to do a whole cycle of the wave to get the wavelength. If I changed the question and I said the maximum distance, the distance between maximum condensations is 2 centimeters, what would the wavelength be? 2 centimeters. If I said the maximum distance between, or the distance between 2 areas of maximum rarefaction are 2 centimeters, what would the wavelength be? But if it's the distance between the condensation maximum and the rarefaction maximum, that's only half the wavelength. You got to go a whole cycle. Okay, how are we doing on that? Questions? Okay, here are a few more review things. Next one. If you know the wavelength, well, let's first of all say, if you know the wavelength, how do you calculate the frequency is what these ideas are doing, okay? But let's do number 2 first. See if you remember from last time. Does cool air or warmer air have a higher sound speed? How did the sound speed, speed of sound in air change with temperature? This becomes really important today as we start talking about wave phenomena like refraction. The answer is that it is higher. Warm air is higher, so B is the answer. Yes, okay. Now, number 3 is a little tricky. Okay. Sound goes from air to water. They have different wave speeds. That wave speed will be the product of the frequency and the wavelength, right? Knowing one, you can find the other, as long as you have the wave speed. But what stays the same as you go from one medium air to another medium water? Is it the frequency or the wavelength that stays the same? We haven't talked about this one, so just throw it out there. Which one do you think? Oh, sorry. The question is, does the frequency increase or decrease or stay the same? Sorry. I combined questions 3 and 4, but we will do exactly what question 3 says. Sound wave goes from air to water. Does the frequency increase, decrease, or stay the same? Okay, stay the same is the correct answer. The frequency is the thing that stays the same. You can remember that. Okay, remember light is a wave also. Okay, colors have different wavelengths and, or sorry, have different frequencies associated with them. Okay, and if a red ball is on the deck of the pool or the red ball is in the water, you still see red. Okay, that's the frequency is associated with that color. Then the wavelength, okay, all right, let's do number 4 before I give away the answer. If a sound wave goes from air to water, is the wavelength going to increase, decrease, or stay the same? This is a tricky one. We have a nice, good assortment of answers. So let me write this up. Okay. So we have the wave speed, which depends on the material properties, defines the relationship between the frequency and the wavelength. Okay. Or we could rewrite it to say that the wavelength is the wave speed divided by the frequency. So in this case, the frequency stays the same. The wave speed increases. So what has to happen to the wavelength? It has to also increase. Okay. But the frequency is the same, frequency stays the same between the 2 media. The wavelength is the thing that changes to correspond, to compensate, so that that relationship, that the product of the frequency and the wavelength is the wave speed stays. Questions about that? No, sound travels much faster in water. 5 times faster almost in water. And about 6 times faster like in rock. So air is actually, the gas is at the lowest, typically the lowest wave speed.
So what would the answer be for 4?
The answer for 4 is A. Yes, you may always ask me that because I do sometimes forget to be clear. Okay, all right. So now let's do number 5. Calculate the wavelength of a 1 kilohertz sound wave in water. Get out your calculators if you like. At least write out the numbers so you can practice. All right. Okay, the answer is C. So questions about that? All right. All right, so that's kind of a review, getting our brains going again after President's Day weekend, remembering these important things about waves, because we're going to use these words and these concepts as we go through our class today. Sound waves. Okay. This idea of wave fronts. Okay. I have some of your learning activities today. See if we can get some help with these. These are some definitions, but I want to get them in your own words. Okay, so let's see. Is Raylan Canty here? Hey, Raylan, tell us about wavefronts. What did you observe about wavefronts, or how would you define wavefronts?
I don't really remember what I said. Were wavefronts just
So what?
sorry, were wavefronts just like the top of the wave moving? Is that
Yeah.
kind of- okay.
So like one point on the wave.
Yeah,
The
like a
ones that were
crest.
easiest to see were the crests. Yep. Okay, good. But any single point on the wave, you know, if you kept that either at the peak or the trough or a node, whatever, if you stick that and followed it as it moves through space, that's what we would be doing as we define these wave fronts. So in my picture here, these green circles represent wave fronts. The distance between them is lambda, the wavelength. So that means that these wave fronts correspond to, say, peaks, right? Regions of maximum condensation, because there's one wavelength between the wave fronts.
So when there are waves happening, you have kind of two different situations. You have like a surfer who stays on the peak the whole time versus like driftwood that like stays in one place as the wave goes. Which
Yes.
one is the wave front?
Oh, that's a really good analogy. So I'm going to repeat it just to make sure everybody can hear it. So she said, if you think about the waves in the ocean, a surfer is trying to ride that peak crest, right, as it travels. That would be like sitting on one of the wave fronts, watching one of the wave fronts move out in space. Whereas driftwood it stays mostly in one spot and just goes up and down. Right, that would be like in sound. That would be like the individual chunks of air just moving about their equilibrium position as the wave passes through. That's a very good analogy. Okay, good. Questions? Yes, please. The wave fronts are the green lines in this picture, yes. And because it's hard to always draw those, you know, curved surfaces, often we talk about a ray, the direction the wave is going, we often draw it as just a ray, which are the orange lines here, and they would be perpendicular to the wave fronts and tell us the direction the wave is traveling. Because otherwise you're up here drawing all these circles, right, as opposed to just it's going this direction. It gets a little more, as you saw in the simulation, right, where things started interfering. So when we draw rays, then you can imagine these wave fronts. Okay, good. Other questions about this idea of wave fronts? Rays. So how does this idea for strings and sound waves relate? Okay, we've seen this before, but just to be really clear, the waves on strings, ropes, drum heads, what we'll be looking for as the wave passes, okay, is the displacement, the change in displacement, either over time of a single, you know, point, or at one instant in time over a string or a wave front, a drum mode or whatever. Positive and negative displacement, but with sound waves, that displacement of the particles corresponds to changes in pressure, which is actually what we're going to talk about more as sound pressure. Questions about how I can represent a sound wave like this. It's really like this. Or why I. Thoughts about that? Yes, please.
In a string, the nodes are the place where it doesn't move. But on the pressure wave, there's still movement or
Right. So the idea of nodes and antinodes is good if you're just taking a snapshot in time, or if you're talking about a standing wave, a repeating pattern like we did with the jump rope, right, where it repeats and you can see that something stays, some point stays still. When we have a wave that's traveling, right, those crests of maximum condensation, then the nodes, and then maximum rarefaction will travel through, right, through the medium. So it's not like if this was a wave traveling, that this point would never move. But if it was a standing wave, and that, a repeating pattern, then that point would never move. So there's two ideas there. Good to clarify. Okay, other questions? Okay, so positive and negative pressure. We said a vacuum is zero pressure. How can we have negative? Trick is right here. It's just relative to the average. Like without the sound wave traveling through, there's some average pressure, and then it's more or less than that average, but we call that positive and negative. Our zero line on the pressure graph here is the regular atmospheric pressure. Other questions? Please. Typically for what we're doing, it's the shape of it that will matter most. Yeah, but the negative implies that it's less than average pressure. And the positive is greater than average. Okay. So, law of reflection. We'll do a little light demo. Okay, so in my mirror, right? You're used to reflections in the mirror. If I take my laser light and I shine at my mirror, then it winds up over there on the wall, right? Now watch what happens. I'm going to do this from straight on the mirror as best I can. I'm going to start going sideways. What's happening to my green dot? Okay, so this is teaching us the law, showing us the law of reflection. Okay, that relative to right here, straight out from my mirror, whatever angle I put this at, that's the angle the reflection is going to go, right? So I'll start with it pretty much straight on, and then I start increasing that angle of incidence, and my reflected angle then also increases. It goes high enough not to, but anyway. Okay. All right. Yeah. Questions about that idea of reflections? Sound waves do the same thing. Okay. So if you had a directional sound wave, like a bat, when they're doing echolocation, they have this narrow beam of sound. Okay, when it goes and it it goes out like this, but then where it comes back from, how it reflects back tells them about their environment. We'll just watch a teeny bit of this, but this is a person who is blind who uses echolocation. You can watch some more of it. See if I can get to where he's doing it. Unmute. Right. Trick is that it's almost impossible to do. Okay. Anyway. Okay. All right. Well, you'll have to look at it yourself, I guess. But they, the link is on the webpage. But the idea is that even people can learn to use echolocation and with their ears detect where the reflections are coming from, just like bats do, which is pretty cool. So this is the law of reflection that I just showed you, but in another kind of picture, okay? So with light, like I did with the mirror, is theta sub I, theta being one of the Greek letters, is the angle relative to a line sticking straight out of the mirror. That's the angle of incidence, and that will equal the reflected angle. Sound waves do the same thing. Okay? You observe that in your learning activity with the wall. Any questions about that idea of the law of reflection? Okay. All right, so in your reading, you talked about regular or specular reflections versus diffuse reflections. Anybody remember what is the difference? Yes, please.
Regular reflections are kind of like through a mirror where it's exactly equal and it's a flat space that's reflecting on.
Right.
And diffuse is like if there's an uneven surface that it's bouncing off of.
Exactly. Thank you. Okay, so I will just tell you the answers to these as I talk. Okay, so the left one would be a regular reflection where the reflected angle equals the incident angle. But then if you have a bumpy surface, basically every part of the wave that hits will reflect at slightly a different angle, right? Okay, who's ever been to like a big cathedral or a fancy concert hall where there's lots of ornamental molding or fluted columns, right? What does the sound like in that place?
It's very echoey and there's just a lot of like the smallest noise is reflected from every angle.
Right, so you can hear it everywhere. That is what you're thinking of when you're thinking diffuse reflections. Okay, so it's more than just fancy to look at. It actually helps spread out the sound. Because in a concert hall, for example, you want the entire audience to get a nice, full, rich sound. You don't want them thinking, wow, that trumpet is really reflecting off this wall, right? Okay, you want it all spread out and mixed up.
So it looks like in the picture, they're all bouncing off of the peaks, right? It's all like the object. Is that how it works? Because it looks like it's off the highest.
Yeah, there would be, these rays again are representing those wave fronts. So there are points of the wave fronts in between these that would bounce off all these other parts. This is just the way they drew it. But at every one, right, if you like drew a line perpendicular to that surface, the angle, the law of reflection still holds, but it would be true down here and all of these others too. The wave will just hit those, the ones that stick out more first, but any sound that keeps going will bounce off the other ones. Good question. Yes, yes, yes.
So in like recording studios, the walls often have a texture and usually because of that texture, you would assume that it would have better acoustics. Is it the material that changes it to be more damping?
Yes, so the goal in recording studios typically is to limit the reflections. Because you don't want the echo necessarily, you want just the straight sound. Next week, or I think next week, anyway, twice for your labs, you get to go into our anechoic chamber to see where our room where we try to limit all of the reflections. But the good sound recording studios are trying to do that. So they put materials on the wall that are absorptive to the sound. This here is assuming a relatively hard surface.
So the texture in that case doesn't matter, it's just the material.
The texture may be helping actually absorb some of the sound too. Yeah. Okay, yes, sir.
So would a specular reflection be like when you go to a museum and there are the two, like the echo, kind of, they're like dents in the wall, and
Uh-huh.
people sit there and you can hear each other whispering across the room?
Yes, and it's the curved shape that is the key there.
Okay.
And I'll show a picture of that in just a second. Yes.
Yeah. So just to clarify, like in like a concert hall or something where you want the sound to like reach everyone, like you said. They would try and create like a diffused reflection, so it doesn't.
To have a diffuse sound field. Mhm. So both the answer to 6 and 7 are diffuse. Okay, so as you were saying, concave surfaces have a tendency to focus the sound because of this law of reflection. Okay, and so if you've been to the tabernacle and heard the pin drop, okay, or if you go in our planetarium upstairs with the curved dome, or your Capitol, or sometimes even museums, like you can't hear the sound and then you walk and all of a sudden you can hear the sound. Often there's a little dome up there, right? It's focusing the sound in one spot. Typically, that's not a desirable acoustic feature. It's an interesting acoustic feature, but it's not typically what you want. When the conference center was first built, you know, if you've been there, the back wall is a concave surface, right? And so story is that when the brethren were sitting up on the stand and the sisters that sit there, they hated the concert hall, the conference center acoustics at first because it was so noisy. Because it was one of those cases where the architects didn't necessarily listen to this sound, the acoustic engineers about their recommendations. And so you had this nice concave reflecting surface that took all of the audience noise and reflected it right up on the rock. Okay. So they called Dr. Leishman and some of his students, and they went up and took measurements and made recommendations for absorptive material to put on that back wall, because they weren't going to change the shape. They needed to dampen the sound as it hit it so that it wouldn't all just reflect right back up there. You know, right where people, with Brother Mercy. So that reflections from concave surfaces are an important thing, and usually not desirable in a listening space. Okay, echoes. Okay, an echo is a very special kind of reflection. I'm going to give some examples here. I'm going to go ahead and draw on my iPad so it's easier to see. Okay. All right, so the idea, echoes are a type of specular reflection, or yeah, regular reflection. But you have your wall here and your sound wave coming in. Remember, these rays are representative of the wave fronts. Okay? And then that bounces off and comes back. Anybody have a good, like your favorite echo experience ever? Yes,
In the Grand Canyon, there's a football that is based on the Grand Dome.
like a curved surface. If you stand at the right spot, all of those reflections are just really coming together. Yes, hey.
There's a room in the government building in Romania that has phenomenal acoustics. We have a video of an elder singing and it's so cool.
That's good. And one of our labs, we get to go in our reverb chamber. So if you want to sing in there.
So in walls and yellow clocks.
Chichen Itza walls, yes.
The racquetball courts in the RV, I was walking with my cousin once. He just like leaned in, stuck his head in, and like kept the door as close as possible and started singing. I was like, whoa.
There you go.
Super
You
echoey.
can see that, right? All of those reflections are. So my favorite echo experience was we were in Germany, up in the mountains, and there was this beautiful Königssee. It's the King's Sea, and there's only been electric boats allowed on it since like the beginning of the 20th century. So it's this pristine lake. And so we take this boat ride out across the lake, and halfway through, the trumpet player plays, right? And you're in this canyon, right, with these really super steep walls. So that's what we're kind of thinking about when we're talking about echoes. Okay, so if I'm standing here, we'll pretend I was playing trumpet or something loud, clapping my hands, some loud sound, that sound's going to travel to the wall and back. And what do you usually like measure if you had an echo and you were like measuring something? What would you measure? The time, right? So let's say I measured the time. Okay. Let's say it's like 2 seconds between my clap and when that clap comes back. All right. How could I figure out how far away that wall is from knowing the time? Yes, please.
1 second for it to get to the wall.
Okay, it will take 1 second to get to the wall. That's exactly right. Okay. And then what else do I know about sound traveling in air? Yep, so we can have our speed of sound estimated at 340 meters per second. Okay, and that meters per second reminds us that speed is distance over time. So I could solve for the distance to the wall. Right, that will be the speed times the time. So that means I would have my 340 meters per second. And we already decided it only takes 1 second to get to the wall. So that means that that wall would be 340 meters away. Yes,
Is that why in movies, they like drop something down a hole to see how deep it is?
exactly. That's another excellent example of using this idea of an echo, right? Because how far down it is, if you count how long it takes to get the echo, then you could figure out how deep something was. Same idea, just turn it on its side. Okay, all right, so let's take a minute. Now this next one, Actually, let's do number 9 first. On your sheet, okay? Number 9 is now talking in terms of milliseconds for the time. Okay, since that's similar to the one we just did. Okay, so the time for an echo to be heard is 20 milliseconds. And that little m, that milli, means 3 decimal places. Take your decimal point and you moved over 3 places, get seconds. Okay, so go ahead, get out your calculator on your phone or whatever, and tell me how long or how far away is that reflecting surface? How are we doing? I'm seeing all of the answers, so we'll go ahead and write through it. Okay, like we said before, the distance is going to be the speed times the time. But what time do we need to use? This is the time for the echo to be heard. So if I use that time, then I will get 6.8 meters. Is that the distance to the wall? That is the distance traveled, but that means to the wall and back. Okay. And then I do this math in my head. If I'm ever wrong, somebody tell me, okay? So the distance to the wall has to be half that. Oh, so 6.8. So you can half the time before you use it, or you can half the distance after you use the time. Either way, somehow you got to remember that it's going there and back. Yes, please. Yes, speed of sound and air of 340 meters per second is something we will use throughout our class. Good question. Okay. All right, other questions? Okay. Number 8 is just the opposite of that. So I will go ahead and put that in the video review for you. But I believe the answer is C. But I will put it in the video for you so we can go on to Doppler here. We want to make sure we do an example of Doppler while we're here. Okay. Somebody tell me, when do you experience Doppler effect most often in life? Yes, please. When an ambulance goes by. Good. Anybody can do a good sound effect for us? What it sounds like? Come on, somebody's got to be good with noises. Yes, go for it. There you go. Okay, thank you. Appreciate it. Okay, so there are 2 things going on. One is that the amplitude changes with how far away the ambulance is, right? Just the things that are far away sound quieter than things that are close. But the second thing that's more unique is the Doppler effect changes the frequency of the sound. Okay, so this thing's going to make 1,000 hertz tone, which isn't necessarily pleasant to listen to. But then when I swing it towards you and then away from you, you should be able to hear the pitch changing. Okay. So what did we observe there? Did you tell? Okay, did the pitch change? Yes. Okay. Was it higher or lower when it came towards you? Okay, so higher when it's coming towards you, lower when it's going away. Okay. But what about how fast I was going? Did that change how much the frequency changed? Did it shift more when I was going faster or slower? When I was going faster. Okay, so that intuition right there is what you need to hold on to as we do the math. Okay, because that will let you know if you have the right answer. Okay, you can always check yourself. If it's moving towards me, it should be higher frequency. If it's moving faster, it should be a bigger change in frequency. Okay. All right. So it depends on the frequency of the sound. It also depends on how fast the motion is. All right. So for the Doppler shift, okay. Yes, please.
Is it both a bigger change in frequency and amplitude as it comes closer?
So the amplitude will only depend on how far away it is from you, not necessarily how fast it's going. It will get closer to you faster if it's going faster. So the rate of change would be different, but the amplitude is related solely to the distance, not the speed. Good question. Yes. Please. Yes. Okay. So towards is going to be increase in frequency. Okay, and away is going to be a decrease in frequency. And that change in frequency is what on your handout is referred to as delta, the Greek letter delta F. That change in frequency is the speed of the object that's moving towards or away from you, divided by the speed of sound in air, 340 meters per second, times the frequency that the object is emitting. Okay. But that's only the change in frequency. That is not your perceived frequency. Okay. Perceived frequency is the second equation on your handout that says your perceived frequency is equal to the original object's frequency plus or minus that change. Okay, so if it's coming towards, you're going to use the plus, and if it's going away, you're going to use the minus. Yes.
So when you're spinning faster, is that just a higher change in frequency, or is that just a higher
Yes,
frequency?
because this V object right here is higher. So that creates a larger delta F. Okay, so that will make it, that's why the change is more pronounced the faster something is moving. Doppler shift happens with light as well. You may have heard of the red shift. Galaxies that are moving away from us are red shifted, meaning their frequencies are lower. Red is a lower frequency than purple. Yeah.
What is F object again?
Whatever frequency the sound is being emitted at. So like for that, it was 1,000 hertz tone. So this is the frequency being played. Right, so the ambulance and stuff, they have a lot of frequencies going on, but each one of those frequencies will have a different shift based on the original object's frequency. Questions? Yes, please.
Can you explain one more time, how influence is affected?
So the Doppler shift is not directly related to amplitude. Doppler shift is describing this change in frequency. You perceive when an ambulance comes by that it also gets louder because it's getting closer to you. But that's just how far away something is type influence, not necessarily the Doppler shift. Okay, so go ahead and start on number 12 here while I find a picture of what's going on. All right, so I'll just draw it. Okay. So the idea is that if you have your sound source that I'll draw here as a star, and here you're standing, okay, then when that, I'm going to do it moving away from you because it will be easier to draw. Okay, let's say it puts out a wavefront, and then it moves a little farther away, and then farther away, and farther away. And every time it puts out that wavefront, then basically they get farther and farther spread apart as it's going farther and farther away, because the new ones have to travel farther before they get caught up with the original ones, right? So that is why, and our frequency is our interpretation of this wavelength. Okay, so if something is backing away from you, the sound it emitted here and the sound it emits at later times are going to have a different period. They're going to reach you at a different rate. Yeah.
Where it talks about like water and they like something out of the waves, so like that.
Yes. That idea of the wave fronts getting closer together when you're moving towards something and farther apart when you're moving away from something is exactly what we're talking about.
So like with speed then, like, is it still happening, but we just don't recognize it? Like how it like how the pitch will change or whatever, like, does it still happen if it's going slower and we just don't register it or?
Yes. Yeah, so her question was, if it's going slow enough, we might not register it. When we start talking about the ears, we'll talk about just noticeable differences. And like our ears, depending on the frequency, don't detect like 0.1 hertz changes in frequency. It's more like a couple hertz change. So there is a threshold below where we would not detect this. Like if I'm just walking away from you, right, then that's not enough for you to experience a Doppler, right? And if I walk away from you singing a single note, right? Because I'm going so slow relative to the speed of sound. Okay, all right, so I'm going to quickly write up number 12 and 13, okay? And then I will explain them more carefully on the video that I make for you. Does everybody know where to find that? Okay, so the speed of the object, the ambulance, is 3.4 meters per second. The frequency is 1,000 hertz. The shift in frequency will be that 3.4 meters per second divided by the speed of sound in air, 340 meters per second, times by 1,000 hertz. You can do that on your calculator. You get 10 hertz, I believe. And then 13 says perceived pitch. So that's using our other equation. Okay. Then that will be the original frequency 1,000 plus or minus that delta F. So if the ambulance is moving away from the lister, do we add or subtract? The subtract is if it's going away, and the plus if it's going towards. All right, we didn't have a chance to talk about diffraction or refraction today. So you can look at the definitions on the slide there online or in your book, okay? But in just briefly, diffraction is spreading out of a wave. Okay, and low frequencies diffract more. They bend more around corners, under doors. Diffract a lot more. And then a rhyming word that is refract, which is the bending of sound waves due to a change in the wave speed. Okay. There are many examples of this, a straw in a glass, you know how it doesn't look straight. That's the refraction, okay, for light. But the key thing is that the wave bends towards low sound speed. Okay, so is it going to bend towards cold air or warm air?
Towards cold air.
It's gonna always bend towards cooler air. So that's why sometimes you hear the train or the marching band and sometimes you don't. Okay, if the sound's here and it's coming out in all these directions, if the cool air is on the bottom, those rays will all refract and keep the sound close to the refract and keep the sound close to the ground. But if it's warm air on top, it goes the other way and takes it up into the atmosphere. You ever wonder why sometimes you can hear things and sometimes you can't? Okay, so it would be like, and then it doesn't get. Yeah, I will talk more carefully through all of this. I will post these also, but then I will write it out all more carefully.